Welcome to this session of our ICDC Summit. My name is Alberto Pagano. I work in ABB as application leader for distributed energy resources application. And our session today will be focused on the energy storage system and in particular on the batteries. We're going through the following topics. We will have an introduction about battery energy storage system. So why are we here talking about battery energy storage system? Then we will see what are the different chemistries we may find in the batteries and what is the implication in terms of protection and switching from different batteries topologies. We will also have a look at a real example, a 4 megawatt BESS installation, where we will see what are the solutions in terms of protection and switching technologies for this kind of system. But let me welcome our guest today, Federico Resmini, ABB Global Product Manager for Energy Storage. Welcome, Federico. It's a pleasure to have you here today.
Thank you, Alberto.
Listen, Federico, let me start with a number, 50%. Analysts are foreseeing the final usage of energy by electricity will reach this number, 50%, over the next 20 to 30 years. This is an enormous incremental number because today electricity is just accounting for 20% maximum of the final usage of energy. What are the drivers of this journey? We need to look at the sectors which are the main contributors in terms of pollution. So we refer to transportation, we refer to commercial and industrial manufacturing and processing, we refer to residential heating. In 2015, in United States, out of 5 billion tons of CO2 emissions, 1.9 were allocated to transportation sector, 1.4 to commercial industrial applications, and finally 1 billion tons of CO2 were allocated to residential heating. So the transformation towards e-mobility, the adoption of electricity for heat generation, and the integration of renewables and the new promising hydrogen renewables application will be the main driver of the electricity consumption. Another key number we should care about is 60%. Solar and wind are expected to account for 60% of the power generation by the next 20 to 30 years. This will be a tremendous number compared to today's scenario. It will also introduce challenges for the grid in terms of stability, in terms of balancing of the system. So Federico, I really would like to hear your opinion concerning the role of the battery energy storage system in this scenario.
Thank you, Alberto, for this question. Yes, for sure the renewables are a challenge for the grid. So today we see two of the major renewable sources, which are the solar and the wind, which are unpredictable by nature. So they are depending on climate condition. And so the power generated by these sources may change. So this is impacting the grid stability of the infrastructure. So this is for sure a limit which is restricting the wide-scale integration of renewables into the grid, and especially in the power generation landscape. But this is not the unique limit or challenge that the grid infrastructure is facing today. There are also other issues like, for example, the state of deterioration of the grid infrastructure, the cost which is unpredictable on the fuel. And then we see, for example, the inability of some utility grid to respond to load demands which are unpredicted and changing versus the time leveraging on the power generation system. So all of these factors are boosting the need to improve the grid infrastructure. And this is helping the door to new technologies coming in the market. Like, for example, coming back to your question, the battery energy storage system, mainly called as BESS. So battery energy storage system can offer various advantages, though they can enable a flexible operation while ensuring the power quality and reliability on the grid side. They can offer many advantages, new ancillary servicing, opening new value proposition and revenue streams. We see, for example, the fact they can reduce the cost on the electricity, on the production side, on the generation, the transmission, and the consumption of the cost of the energy. Then we see, for example, other important advantages on the stability of the grid, the quality on the grid, because they can leverage on a power source and power generation system to react quickly against changes on the demand side, on the load. They can also increase the reliability of the grid, providing a power availability against unexpected outages, mitigating the risk, of course, of having outages on the grid. While they are, as we said before, facilitating the integration of the renewables into the grid, smoothing this kind of unpredicted power generated by these sources, while they are also reducing the emission and the impact on the environment, like the CO2 emission, for example. They are normally embedding a system, an energy management system, which is offering different functionalities to the different stakeholders, like we see the utility grid, but also the customers. One important part of the battery energy storage system is, of course, the battery. So now let's change the topic. Let's enter into a bit more details about the DC side. So I'm going to speak with Enrica Micolano to present some features around this topic, around the battery technologies and the challenges that we face when we have to design the DC protection architecture around the whole architecture. So thank you very much for your question. We already saw before the advantages of a BESS, energy storage solution. Let's now dig into more details about the battery used in the BESS system and the challenges that we face when we have to design the DC electrical protection. So let's start saying that unfortunately there is not one battery working for all the requirements, able to cover all the needs. We see, for example, in the market different types of battery technologies, not limited to lead acid, nickel cadmium, sodium-based, lithium-ion. So various technologies are available in the market today. For example, if we take then one of these technologies, then we can split that into different subcategories depending on the chemistry mix, the cell construction, the cell geometry. Taking a lithium-ion world, we see 6 main categories. We see the lithium cobalt oxide, LCO, the lithium manganese oxide, LMO, nickel manganese cobalt, NMC, nickel cobalt alumina, NCA, the lithium iron phosphate, LFP, and lithium titanate, LTO. All of these batteries are providing different features and performance, which are depending on the chemistry mix on which they are based on. And we see different factors which are very important when you need to select a battery to cover the need on the requirement on the application. Taking, for example, this lithium-ion, we see important factors like the energy density, which is the amount of energy that can be stored into a battery, or the power efficiency, which is the rate at which the energy can be transferred in and out of the battery, meaning charging and discharging the batteries. On the BESS system, what we see today is that the technologies mostly used are lithium-ion phosphate, nickel manganese cobalt, and another one which is the sodium-based, the sodium sulfur, mainly because of their superior energy density and cycle life. So we are here today with Enrica Micolano. Good morning, Enrica. Enrica is the senior researcher and the responsible of the laboratory for energy storage within RSE, which is a research center in Italy. Can you explain which are the main challenges or the main features that you see among these 3 technologies we have mentioned?
Thank you, Federico, for your question and your introduction. Today, lithium-ion batteries have the best performances among all the electrochemical accumulators. They are used for every kind of applications, from electronic devices to electric vehicles, UPS systems, home batteries, and grid-connected energy storage applications. As you already explained, the term lithium-ion battery refers to a technological family, including many different subcategories that can be differentiated on the basis of the chemistry, geometry, and construction. So the term lithium-ion battery refers to a technological family including many different subcategories that can be differentiated on the basis of the chemistry, geometry, and construction. It is possible to find and to buy cells, modules, and energy storage systems with very different performances, and it's very simple to realize and to adapt the energy storage system realized with this technology to the applications that it must cover. One of the strengths of this technology is in fact its great versatility and modularity. The mainly used chemistries for applications that require very high performances, such as the electric vehicles and the grid-connected energy storage applications, are, as you already said, the nickel manganese cobalt battery and the lithium iron phosphate battery. The first technology is characterized by very high performances, especially in terms of energy density that can reach 240 watt-hour per kilogram, and in terms of power density that can reach almost 1000 watt per kilogram. And also the lifetime is very good because it can be around 6000 charge-discharge cycles. The weakness of the NMC battery is a relatively low intrinsic safety level. On the other side, the LFP battery has in general lower performances than NMC, but always very good for an electrochemical accumulator, but its cost is lower and the intrinsic safety level is good. Another technology that is very used for grid-connected stationary applications, for example, for the integration of PV and wind generators, is the sodium-sulfur battery. This battery belongs to the family of the high-temperature batteries, so-called because their internal temperature, operating temperature, is very high. It is around 300 centigrade degrees, necessary to keep the electrodes in a molten state. This technology is very different from lithium-ion battery that is very modular, because sodium-sulfur battery is produced only one manufacturer in the world, and it is possible to buy only a containerized battery system with a very big size, starting from 1.2 megawatt-hour on, and already equipped with auxiliaries, protections, battery management system, and power electronic. The performances of this technology are always very good because the energy density of the cell is around 200 watt-hour per kilogram, and the lifetime is also very good. The same as lithium-ion battery, also the sodium-sulfur battery has a low intrinsic safety level. This means that for both the technologies, it is necessary to integrate the energy in the energy storage systems, the proper protections and battery management system in order to reach an adequate level of intrinsic of safety and to avoid abuse conditions and manage the system in a correct way.
So, thanks Enrica for this description. Then we can also say that from the battery technology to a battery product, there is a long run, right? If we take a technology and we build different battery products on the same technology, we can see different features, different performance. So that means that it's very important also to study the battery system on this construction side, also when it comes to the design of the DC electrical protection architecture. So for example, if we take a product on lithium-ion, we see that we start from having lithium-ion cells, assembling this into a battery module in series and parallel connection to get there a first level of battery management system, which is managing the parameters of the battery cells, like the voltage, temperature. Then we connect these battery modules in series to build up a battery rack to achieve the voltage that is needed by the power conversion unit that needs to be connected. Again, in this case, we have another level, another layer of battery management system. On top of that, then we need to connect in parallel different racks to achieve the energy and the power needed by the application. And again, in this case, we have a third layer of battery management system, which is managing all the racks down to the single cell. And when we look to the DC electrical protection, we see more or less the same story. So we have different devices from fuses to breakers integrated down from the battery module to the string and to the battery system level. So the big challenge here is then to work around all of these factors to design the right protection on the DC side. For this reason, I would like then to raise another topic to you, Enrica. Can you explain us how do you solve this challenge? How can you find the right coexistence between all of these products, all of these parts from the module and the cell level to the rack, to the system level, but then also to the integration within a system with other power conversion system and other device connected?
The main problem with energy storage systems is the short circuit. The short circuit of a battery is a very dangerous event because it can determine the destruction of the battery itself. In fact, the increase of the temperature very fast can determine the melt of some components of the cell or of the module, and in the worst case, it is possible to reach the thermal runaway. It is very important so to proper manage this event, to prevent it and to stop it very quickly in case of occurrence. The short circuit in an energy storage system can occur at every level, at cell, module, rack and DC bus. And it is necessary to evaluate all the possibilities and to implement in the energy storage system the proper protections at every level. This is why many manufacturers include for example, at cell or at module or even cell level, some internal protections able to avoid the short circuit at the terminals of the module. Some protections can be, for example, fuses or weak parts of the circuit that can melt due to the over temperature. The problem with this protection is the fact that they cannot guarantee selectivity. In fact, they can be faster than external protections, determining the outage of service of the whole system. Besides, it is not simple to restore the system in case of fault, because it is not easy to identify the broken module or the broken cell in an energy storage system realized by a great number of elements, and sometimes it is necessary to replace the broken element. To guarantee the selectivity, it's necessary to ensure a good coordination between the internal and external protections. For example, first of all, external protections should be faster than internal ones. The study of the short circuit current of the battery is very important during the design of the energy storage system and during the sizing of the protections and the elements of the system. During the fault, the current of the accumulator reaches the peak power almost immediately. Then the value of the current gradually decreases for a few seconds. The peak value of the current can be calculated as the ratio of the initial voltage at the terminals of the battery, of the accumulator, and the sum of the internal ohmic resistance of the battery and the resistance of the external circuit. The internal ohmic resistance is an intrinsic property of the accumulator, of the cell. Its value can change and it depends on the chemistry, the geometry and the construction of the cell, and also on external factors and operating conditions. For example, lithium-ion batteries that are realized in many different sizes and formats can have an internal ohmic resistance of around from 0.5 million per cell to more than 10 million per cell. And it is very important to evaluate this parameter during the sizing of the module. The situation is different for sodium sulfur battery that, as you know, is realized in only one configuration and size. The internal ohmic resistance of the cell is around 3 million, and its value is very strongly dependent on the internal operating temperature of the battery, of the module. Another point to consider during the sizing of the system is the fact that the internal ohmic resistance isn't constant, but its value can depend on the state of charge of the battery, on the aging, and of the external operating temperature of the battery. In fact, its value can increase with aging, can be double at the end of life of the system, and increases also when the battery works at low temperatures and low state of charge. The value of the internal ohmic resistance for a cell is not constant, but can change with the state of charge, the temperature, and the aging of the accumulator. For example, its value can be double when the battery is at the end of life, and can increase significantly when the battery works at low state of charge and at low temperature. This means that it is necessary to consider this issue because the correspondent decrease of the fault current can determine the failure of protections. The consequent reduction of the fault current due to the increase of internal ohmic resistance can determine the failure of the protections. So it is important to consider this issue during the design of the energy storage system. Another challenge is to consider the parallel functioning of many racks on the same DC bus. In this case, it is necessary to evaluate all the possible faults that can occur. For example, you can have a fault on the external terminals of a single module of the rack, and in this case, it is necessary the intervention of the internal protections of the modules, because the current flowing in the external DC protection is too low to allow the intervention of these protections. In this case, it is necessary that the BMS would be able to detect the fault and to act on the external protections in order to avoid anomalous working conditions for the rack. In case of faults on a single branch of the rack, external to the rack, or on the DC bus, it is necessary, first of all, that the external protections should be faster than internal ones in order to avoid the outage of service of the whole system. Then it is also advisable to have protections on a single branch with, for example, a double threshold of intervention with opening times inversely proportional to the current in order to allow the interruption of a single branch and avoid the outage of service of the whole system.
Thank you, Enrica, for your contribution. Let's go now to speak with Alberto to conclude our conversation, to see a real case on the BESS configuration and the design around the DC electrical protection. In the meantime, I take the chance to thank you and to say hello. We will see each other in the next event. Thank you.
Welcome back to our energy storage session. Hope you found of interest what Federico and Enrica showed us concerning chemistry and protection strategies of batteries. What we are going to see now is a concrete and real use case where we'll explore the possible solution in terms of protection and switching devices to protect the entire BESS system. So, as you can see, here we have a real example. From right to left, you may see the battery racks, which are then coupled into a DC combiner panel. Then we do encounter a recombiner DC panel. Then power is converted from DC to AC through a PCS, power conversion system, which is then converting power to the medium voltage utility. What we see here is a typical example of a 4 megawatt installation. In terms of energy, this may easily reach 2 megawatt hours of energy. The rated voltage of the system is 1500 volts DC. That is a very important rated voltage, well established in solar application and becoming the standard voltage reference also for battery energy storage applications. The system is what we may call a typical utility side of the meter energy storage application, where typical features and functionalities needed are peaking capacity, renewable firming, arbitrage, and black start, high landing. Let's now focus on the battery racks. The battery racks in our system may be around 20 different battery racks, which are arranged then in a 4 modules containerized architecture. Each battery rack provides the battery modules, in our case lithium-ion batteries, together with an appropriate protection and switching device. From a safety standpoint, it's extremely important to select the proper device to protect and switch the battery rack. In our specific case, a multi-level protection is provided, having fuses at cell level, rack level, plus a switch disconnector, which combined with the fuse protect from overcurrent and short circuit the battery rack. Let's have a look at the protecting device we are installing in this application. As you may see, we are installing a switch disconnector. In particular, it's a T-Max T4 PV switch disconnector rated at 1500 volt DC. The switch disconnector, together with the fuse installed in the battery rack, is providing the appropriate level of protection against the overcurrent and short circuit within the battery rack. Moving ahead, we can see the DC combiner panel. This is where an easy parallel connection of battery racks is provided, and very important is the protection strategy we implement for the DC combiner panel. In our case, molded case circuit breakers, T-Max T4 PV rated at 1500 volt DC are provided. They can reach up to 25 kA of breaking capacity, which is required for the application. The breakers are then coupled, and we may encounter an E-Max E4.2 switch disconnector, 1500 volt DC rated. The rated current of the E-Max 4.2 is around 1000 amps. That is one of the latest technology ABB is introducing in the market for direct current applications. E-Max E4.2 switch disconnector 1500 volt DC provides a short time withstand current, otherwise called ICW, up to 100 kA. This is an extremely high value provided by this kind of device, but extremely important for battery energy system application, because this is the expected value of the prospective short circuit current we may have at this point of the system. The 4 DC combiner panels are then coupled by a recombiner panel, where inside we may find still E4.2 1000 amp switch disconnector E-Max 2 rated 1500 volt DC, together with fuses. Upstream, the 4 breakers, we may find an E4.2, in this case rated 3200 amps switch disconnector, always 1500 volt DC. On the left side of the circuit, we may see the PCS, the power conversion system, which is a bidirectional inverter which provides charge and discharge of the batteries. Upstream and downstream, so AC side and DC side of the PCS, an appropriate protection and switching device must be provided. It's not just a matter of protection and switching, but also it's about connectivity, since those devices have to be integrated with a BESS control system. On the DC side, we may see an E4.2 switch disconnector, 1500 volt DC, 3200 amps, which provide overcurrent and short circuit protection in combination with the fuses installed inside the PCS. On the AC side of the PCS, we do have an Emax E9 rated at 3200 amps. The Emax E9 provides a rated voltage up to 900 volts. That is extremely important value because it perfectly covers the 800 volt AC application, which is what we may expect for battery energy storage system which has distributed DC side at 1500 volt DC. But it also covers the plus 10% that most of the utilities require on the AC side of the PCS. E9 is another of the latest release on the market of ABB devices for energy storage application. That's the conclusion of our session. I really thank our guest we had today, Federico from ABB and Enrica from RSE. I really thank you for your attendance, your attention. Now I leave you with a short overview of the ABB entire offering of protective and switching devices for battery energy storage application. Thanks.